This 3D globe shows the physical reality of intercontinental travel. If you want to fly from Europe to Los Angeles or Tokyo, the shortest possible path, the Great Circle Route, arcs directly over the North Pole. But in the 1940s and 50s, taking that direct path was politically impossible. Soviet and Chinese airspace was strictly off-limits to Western airlines, creating a massive blockade known as the Siberian Closure. Commercial flights to Asia were forced into massive, time-consuming detours through the Middle East and India. To bypass that restricted airspace, airlines had to figure out how to fly the Arctic shortcut. That shortcut was a navigational death zone. While the temperatures were lethal, the true barrier was that the standard laws of navigation completely fail at the top of the world. Standard aerial navigation relies on the Earth itself to orient the pilot. But as an aircraft approaches the high latitudes, the physical and geometric properties of the planet start actively lying to the instruments. This is Einar Sverre Pedersen. He was a Norwegian navigator who flew sub-hunting missions for the RAF during World War II, and he suffered from what he called the polar bacillus, a lifelong obsession with the Arctic. Pedersen realized that to safely cross the polar ice cap, human beings couldn't rely on the planet's magnetic or geographic cues. They had to invent a way to navigate that functioned independently of the Earth's rotation and orientation. Meridians converge at the North Pole, crossing straight flight paths at rapidly changing angles. Maintaining true north forces a deadly inward spiral. Pedersen's solution overlaid a grid of perfectly parallel lines onto a flattened map, instantly resolving a curved polar route into a mathematically constant heading. Flattening the sphere on paper solved the mapping crisis. But navigating that grid in the air required flight hardware that didn't rely on magnets. Near the magnetic North Pole, the horizontal pole of the Earth's magnetic field drops to zero. Standard compasses either spin wildly or die completely. To fix this, Pedersen worked with the Bendix Aviation Corporation to implement the Polar Path Gyroscope. This system ignored the Earth's magnetic field entirely, maintaining its directional heading using pure inertia. It featured a manual dial where the navigator inputted the aircraft's current latitude. This mechanical adjustment counteracted apparent precession, the natural drift caused by the Earth rotating out from underneath the plane. Substituting inertia for magnetism allowed pilots to lock on to Pedersen's parallel grid. But gyroscopes still suffer from mechanical drift over time, meaning crews needed a way to visually recalibrate them during the flight. To correct that mechanical drift, navigators relied on celestial navigation, taking visual bearings on the sun or the stars. But the Arctic presents a unique environmental barrier. During polar twilight, the sun sits just below the horizon for weeks at a time. The sky is too bright to see the stars, but the sun itself is completely hidden. To see through this optical blind spot, they used the Kollsman sky compass. Even when the sun is below the horizon, its light hits the upper atmosphere and scatters into invisible polarized ribbons stretching across the sky. The sky compass used a specialized polarizing filter. The navigator would look straight up and rotate the filter until a cross-shaped pattern disappeared. That exact angle mathematically pinpointed the azimuth of the hidden sun. By mastering invisible light, Pedersen completed his navigational triad: the grid, the gyro, and the sky compass. The Arctic crossing was finally viable. Look at this AAS Sapreller plane on the tarmac. Armed with Pedersen's Triad, Scandinavian Airlines system launched the first scheduled commercial transpolar service on November 15, 1954. Two pioneering DC-6B aircraft took off from opposite ends of the route, famously crossing paths in the dark directly over the North Pole. Travel time between Europe and the U.S. West Coast plummeted from nearly 30 hours down to just 16. This single flight bypassed the geographic roadblocks of the Cold War, allowing SAS to connect cities in hours rather than days. The route's success prompted Universal Genève to create the Polar Router Watch, an anti-magnetic tool designed specifically for these crews. Today, thousands of modern jets routinely fly the polar route, shaving massive amounts of time and fuel off global travel. And while today's flights rely on advanced GPS and computerized flight management systems, the underlying software is still executing the exact same grid math that Einar Sverre Pedersen formulated by hand to conquer the top of the world.